The last speaker of this morning is Dr. Pavel POLISHCHUK. Dr. POLISHCHUK graduated from Odessa National University in 2001 and got his PhD there in 2009. And from 2015, he's the leader of the established group of Chemoinformatics in the Institute of Molecular and Translational Medicine at Palacky University in the Czech Republic. His main research interests are the development of chemoinformatic approaches and tools for machine learning and the explainable artificial intelligence, pharmacophore modeling, and de novo design. He's also an author of multiple open source software tools for chemoinformatics. Today, your lecture is about explainable artificial intelligence. The floor is yours.
Thank you. Thank you for kind presentation. I would like to thank Alexander Varnik for such a great opportunity to be here. It's really enjoy to visit Strasbourg once more. And such a great event which was organized in a regular manner. So I hope that no further issues will happen and we will continue to meet each other frequently. Today my topic would be about explainable artificial intelligence or machine learning methods. Already several times during this event, questions appeared about how we can understood or explain these models. And I provide for you for this 30 minutes or a little bit more something like a time travel for 60 years of development in this field. So take your seat, and we are going. So when we start thinking about QSR models, quite frequently, we think about something not understandable completely. Something quite frequently it names black box models. And this belief appeared a long time ago, and it still exists. And we will see how we can look inside this black box. But we will start from the very beginning, from the pioneer work of Hench, where he found a correlation between structural features, not structural, but physical-chemical features, and biological activity. And it's a very simple equation, linear equation, where you can see and where you can, from this coefficient, deduce what knowledge is behind this relationship. And it's quite easy to understand if you want to, for example, optimize your activity to increase it. You should use p-value something around 0 because it is a quadratic term with a negative sign, and you should increase your sigma value, Hammett constant, as much as possible. Of course, it cannot be infinite because it is limited by the physical laws, but it's a way how we can look inside, get some knowledge, and use it to guide our next steps of design. It's very general way how we interpret model, and we get some so-called global interpretation results. So we get some general trends from the model. Another type of models which were proposed very many years ago, it's free Wilson models, which is also a linear model where researchers proposed to apply for compounds, for the set of compounds having the same scaffolds, where every substituent gets its own indicator variable, 0 or 1. And from this coefficient, you again can get an understanding how every substituent influences your activity. It's very easy to understand these models, but unfortunately, they are not very predictive. And they are limited in the case of the free Wilson models by the generic compound series. More advanced approaches were proposed. Here another famous example of ConFi approach, where you should generate 3D structure, put into the grid, align those conformers of different compounds, calculate interaction with the probe atoms put in every cell of this grid. You can use electrostatic probe or steric probe, then create this matrix and apply a PLS model, which is a partial linear regression, to find the correlation with your activity. And the good thing is that these are almost the same linear regression model where you again have a coefficients, and these coefficients can be visualized back on this grid structure, and you can see some favorable and unfavorable regions according to the electrostatic interaction or steric interaction. It's a very nice way how we can again get new knowledge, and we can understand how we should modify our molecules. But again, this approach are not very it is not very good applicable to very flexible compounds. So that's why there's also a lot of limitations, and now it is not very popular. Another self-explaining machine learning method is the decision trees. So decision trees is just a set of rules, logical rules, which can try to explain why this compound has particular property value. I found probably the first publication in chemicals field where researchers tried to classify compounds which are used as solid phase fluorescence enhancers based on their physical chemical properties. So they found that using some longer compounds and which have such a feature of pentavalent phosphor with oxygen or sulfur atoms, you can get some potential enhancer. It's quite easy to understand these rules, but again, those models are unstable and they're not very well predictive. So that's why they're again not so popular nowadays, but we will return to these models a little bit later. So neural networks, when they started to be used in chemical informatics, they showed their superior predictive ability in many cases to the previously demonstrated models. And researchers also asked the question, okay, we already had such a good models which we could interpret quite easily. Can we do this for the neural network models? And here is just again one of the first attempts how we can look inside the neural networks. I will not bother you with many formulas, so don't worry. So you shouldn't track on all of them. I just wanted to show that it is quite easy to calculate, for example, in this case, importance of particular features, those input neurons. And here is an example of application. So researchers model absorbability of 55 organic molecules on carbon fibers. And they built regression model, ordinary regression model, and neural network model. And they used topological descriptors to do this. And only 5 of them were selected finally. And based on the same descriptors, they rebuilt neural network model. And since this relative importance, they do not provide a thing. So we cannot say this is a negative or positive influence. So we can just say that this is more influential or less influential feature. And they suggested that they can use those signs obtained in a linear regression to explain the direction of influence, and calculated the relative importance from neural networks like a magnitude of this contribution. It looks quite nice, but here is another issue happened, because those descriptors which they used, they are not so easily interpretable. So in this case, these topological descriptors are not, they have some meaning, but it's quite complex to understand by humans. So they somehow related to different structural features, and researchers tried to speculate, to somehow explain how the structure influences the activity, but it is quite a lot of speculation, in my opinion. So that's important, that in those cases, we need to use interpretable descriptors. That's really important. Another example, how we can look inside the random forest models. This approach was suggested by my supervisor, Professor Kuzmin. And it is also quite easy. So we can calculate, for example, the difference between the average values predicted in each node of our trees. And this difference would be a contribution of a particular descriptor which is used to split the node on two nodes. And when we have a compound, we can go down this tree and we can gather all these contributions for particular descriptors for particular compound. And finally, we get a knowledge. We summarize all this contribution across all trees, average them, and get information about the contribution of a particular descriptor into particular compound. And if we use fragmental descriptors, we can go back to a structural level. So we can transfer these contributions to atoms and visualize on structures, and we can estimate the contribution of separate fragments. In this case, we studied agonists of 5-HT1A receptors. Here is the general formulas. They were all derivatives of aryl piperazines. And we built two models, one based on PLS approach, another one on random forest. We use the same fragmental descriptors, but for PLS, we used feature selection, so there was just 72 of them. For random forest, we took all of them. We obtained reasonably predictive models, so we were able to interpret them. And we get from these models quite nice structure property relationships. So we were able to rank all these fragments for each of these particular R group, how they contribute. And both models were agreed mostly on these contributions. Yes, numerical values are different, but ranking is almost the same of those molecules. And we discovered that small phenyl substituents in orthoposition is favorable, but for example, in paraposition, substituents are always unfavorable, irrelevant to the electronic nature. And later it was discovered that there are some steric hydrons of a receptor, so it cannot adopt such substituents. The same we observed for the linker. For example, linkers with 4 or more atoms is favorable. If they have less number of atoms, it is unfavorable. And it is also quite nicely corresponds to the knowledge of experts in these fields. So here's just an example how we can get, and here it's important feature that we first get some local interpretation because we got information about contribution to particular structure. And then we go to the global level. So we summarize the contribution of similar fragments across multiple molecules and get this general trend. Another group of approaches are rule extraction approaches. First one is a decompositional group of approaches. The idea behind is very simple. So we can extract rules from models if we know their structure and we can use this structure somehow. For example, for neural networks, it was proposed pretty simple way. If we know these weights and we know this threshold which should be achieved to activate the neuron, we can create different rules to overcome this bias. For example, if we activate B, C, and not activate E, then we get 6, and we can activate the neuron A. And we can combinatorically enumerate those rules and create those quite explainable way how to understand. Of course, here is an issue because these rules can be very numerous, but there are some techniques how to reduce their redundancy. One of the relatively recent papers which were proposed for interpretation of deep learning models with multiple layers, they calculate something similar, not exactly the same, but something similar approach. They calculate rules for between every 2 layers, and then combine them together in one large set of rules. And these rules also can be additionally validated, so they are predictive as well. They may be a little, sometimes they can be complex, but nevertheless, this is a way how we can look inside even such a complex models. Another group of approaches are belonging to pedagogical, or now it is more common to name them surrogate modeling. The idea is also very simple, and this is the first group of approaches which belong to model agnostic approaches. So they can be applied to any kind of models you have. So they are not restricted to neural networks, SVM, random forest, whatever. The idea behind is very simple. So if we have some data points, positive and negative class, we have some hyperplane which separates them, for example, then we can relabel all these training set compounds according to the prediction of a model, and we can then apply some simpler models to make a prediction to build on this data. Usually people use decision trees. So they apply decision trees to this set of points and get relatively simple models which can understand where this boundary exists. More advanced approaches are based on the same idea, but additionally we can enumerate some artificial compounds, okay, objects, it doesn't matter, near this hyperplane to make it more dense, and again apply this simple tree model, for example, and in this case we can get more precisely this boundary condition which separates actives from inactives in our case. I found one publication which is also quite recent, where the researchers use this technique and they get something new from their SVM model. So they model inorganic organic hybrid materials, and for them it was important to understand the condition at which they will obtain single crystal or polycrystalline products. They built SVM model which were highly predictive. It will even outperform human suggestions in the research. But then they decided to look inside this SVM model, build a tree. Here just a part of this tree, and they saw that here are quite nice separation of different kinds of organic diamines which are used to train these models. And they discovered that if they use compounds with low polarizability without sodium or iodine in a solution, if this reaction are quite long, the pH more than 3, and there is no fast cooling, they can obtain single crystal product. Here are just 3 other groups of compounds which were discovered, and so they were able to formulate in a chemically understandable way the reasoning and get some new knowledge. And according to this new knowledge, they selected new compounds, made experiment which was confirmed their hypothesis. Sensitivity analysis, how much time we have? Maybe we can skip this one. Let's go to the next one, so we make time gap. Variable importance. This is another technique which is quite popular, and it is also model agnostic approach. So it can be applied to any kind of model. It can be implemented in different ways. So for example, you can add some noise to your input variable, calculate the prediction, and you can calculate how much accuracy decreased. The higher the decrease, the more important your variable. Another way how you can estimate the importance was proposed by Bremen for random forest, but again, this technique can be applied to any other kind of models. You can just permutate values of your variable, make prediction, and calculate the difference between and calculate how much accuracy dropped. In this way, you can again get the knowledge about how each descriptor contribute, not how they influence, how much they influence your output. But again, you don't know the sign. So you don't know is a positive or negative contribution. So some general understanding you can get from this analysis. Maybe one of the underestimated approaches in chemoinformatics are partial derivatives approaches. They are just local sensitivity analysis, but I separate them in a separate group. They can be calculated analytically for certain models, but they are generally applicable if we make numerical derivation. So the idea is very simple. So we have now a variable, we add some increment to this value, make prediction, and then we simply calculate the difference between predicted values divided by the size of this increment. And this is a forward difference. You can do this with backward difference or central difference. It doesn't matter. No, it matters, of course, because it depends on from which side of a point you estimate your gradient. But normally they should result in something similar. But generally, some central differences are preferable. So these are very popular approaches. And here I present the example from the work of Alexander Warnek, where they applied this, for example, to analyze the inhibitors of acetylcholine esterase. Based on fragmental descriptors, they built a random forest model, calculate contribution of single descriptors. And since these are fragmental descriptors, they were able to transfer contributions to atom and color these atoms with a positive or negatively contribution. And you are able to understand negatively and positively contributed patterns in your molecules. However, this approach applied multiple times before that. And here I just also quite old publication of Gisbert-Schneider, where they estimate the contribution of their pharmacophore triplets and visualize the contribution of molecules. What they do, they just nullify a particular bit in the bit string, which is actually the same partial derivatives approach, where you have just the unit value of increment. So it's the same. And many other papers which were published use this technique, but they did not recognize it properly. So far, so good. So until now, what we can do, we usually have a molecule, calculate descriptor, build our models, and when we want to make a interpretation, we need to calculate the contribution of descriptors, which can be then transferred on a structural level, if it is possible, and if we want to do this to understand structural features which are influenced. And the critical point here is a descriptor interpretability, as I showed you before. So you cannot use uninterpretable descriptors. And the issue here is if we use modern end-to-end models, we do not have these descriptors at all. And that's a question how we can do this interpretation in this way. And is it possible to change the paradigm and skip this intermediate step of calculation of contribution of descriptors and go to the model, from model directly to structure interpretation? And actually, it is possible. There are two papers which were published almost simultaneously, almost 10 years ago. One of them, one of these approaches were suggested by Rinnick and Landrum. And the idea behind that, they remove single atom virtually from structure, get a new fingerprint without this atom. Some bits were nullified, again, calculate the difference, and these are contribution of a particular atom for this particular structure in this particular property. And this is an example of local interpretation. Here is just how it looks like. So they calculated this for random forest, naive bias, and they observed quite good correspondence. for different types of models using the same type of descriptors. Another approach was proposed again by Professor Kuzmin, which we implemented. It is more general because in this case, we virtually remove not a single atom, but we remove some fragments. And these fragments can be really arbitrary. So we can use some connected fragments, or we can even remove disconnected fragments. And in this way, we can, for example, explore some synergistic effect of different fragments in our molecule. So it's just depends on your imagination what to do with this approach. And the idea behind it is the same. We again remove this fragment, calculate the predicted value for counter fragment, calculate the difference, and this would be a contribution of this particular fragment in particular molecule. We applied this approach to multiple tasks. Here I just show one example. For modeling of Ames mutagenicity, we used random forest models and SVM models, and we used two kinds of descriptors, fragmental descriptors, which are serms, and those green are dragon descriptors. We took all 2D dragon descriptors, which contained a lot of non-interpretable descriptors. So those models cannot be interpreted in an ordinary way, which we presented before that. And we show that from quite good correspondence for contribution between different models based on different techniques and descriptors. And we were able to separate toxicophores from detoxicophores in this case, in a quite clear manner. Another example is from the toxicological field, when we try to understand the acute oral toxicity on rats, we quantify the contribution of known toxicophores and some selected fragments, and we identify that, for example, phenylpiperidine has quite high contribution to toxicity. So this is a potentially alert. However, we could not prove this from the biological perspective, but the model suggests that this potentially dangerous feature, and if you don't need it in your molecule, maybe it's better idea to avoid it. Those large distribution of contributions of different fragments can also be explained. So we suggested that this large difference is observed due to the structural environment of our fragments. And we demonstrated this also in a toxicological study, in this case on a Tetrahymena piriformis. For example, we selected halogen atoms and calculate their contributions. We see quite large variation of those contributions and large contributions absolute values as well. We performed Gaussian mixture modeling clustering to separate those contributions. In all cases, we observe some right tail of contributions, and then we separate molecules having high and lower contributions on two classes, apply Smart's minor, and get structural features which separate those two group of compounds. And we were able to identify that those highly toxic halogen atoms, they are associated with the carbonyl group. So these are alpha, they attach to alpha atom, to carbonyl group. So it's quite known toxicophore, and these are just how we can explain such a large variation of those contributions and get additional knowledge from our models. So at this point, we are somewhere here. We started from our trip from not very predictable, but very interpretable models, then goes to high predictable models, but with low interpretability. And now I believe that we can interpret almost all models. So at least in a QSR modeling field. And then appear some deep learning era started and AI era started. And how we can perform in this part of a timeline. There are multiple architectures which were proposed for neural networks, but the most popular ones in chemoinformatics for prediction of molecular properties are multi-layer perceptrons like deep neural networks or graph convolution neural networks or message passing or something like this. And there are a lot of approaches which were developed in the computer science field to understand those models. And these approaches slowly transferred to chemoinformatic fields. And there are so many of them that it is quite difficult to understand. Are they really applicable? Are they really useful? Can they give you some new knowledge, especially relative to the previous approaches? Are they really useful for us? One of these first study where authors tried to answer this question. Since it is quite difficult to use real data, they collect synthetic data sets corresponding to some rules, for example, presence of benzene, naphthyl, some other features or combinations of features. They created those data sets, labeled them on positive and negative samples, built models. In all cases, they were able to obtain very high precision, almost 1 of AUK value using graph convolution method. And they used integrated gradients to calculate the interpretation. So for using integrated gradients, they were able to calculate contribution of every single atoms. And since this, they were able to rank all these atoms and compare with their ground truth values and calculate from this again AUK value, which means how well model rank true and other atoms. And they observed quite interesting thing that not all models, if they're even highly predictable, were able to discover these patterns in data sets. After some additional analysis, they concluded that there were some hidden biases in the data sets, and they're underrepresented. So if they took larger data sets, they could obtain better results. Later, the same group of authors investigated how different models interact with different interpretation approaches. They use graph convolution, message passing, GraphNet, and attention network, and they use multiple different approaches. And they again create these synthetic data sets with artificial rules. They calculated AUK values for interpretation, and it was quite interesting that a lot of methods perform relatively close to the baseline, to the random models in all cases. And more or less stable were integrated gradients and class activation maps. But they also failed on relatively complex patterns to discover them. But this is still a question. This is an issue with the interpretation approach or the issue with the data set. So it's still open. That's why we suggested and created some benchmarks which can be used to validate and evaluate those interpretation approaches. We also created synthetic data sets. There are 6 of them. Some of them were quite simple, using some additive ideas. So we quantify number of nitrogens or number of nitrogens minus total number of oxygens in our molecules, or some specific case when we assign the contribution for nitrogen and the oxygen are equal, and we strictly keep molecules where only the number of nitrogen and oxygens are equal. So, such a case which are more difficult to model, try to fool them. Some amide data sets where we model, in this scenario, since this one are simply predictive properties, in this case, we simulate scenario when we want to model properties like lipophilicity, which can be quite nicely predicted with the group contribution methods. And the last data set was the closest one to the real data sets, what we have. So we classify molecules according to the pharmacophore constraint. So positive molecules should have at least one conformer of them, should have a hydrogen bond donor and acceptor on a distance from 9 to 10 angstroms. And if there are no such conformers, the molecule set to the negative class. So we created this data set. We tried to control biases in this data set as much as we could, but probably this is never-ending story. Those are available on the GitHub, and the paper was published last year. We also proposed several metrics how we can evaluate, because AUC is not much reasonable because it ranks all atoms at once, but we are more interested in the top ranked atoms. Our method can really rank those atoms on top of others. And RMSE, if you want to calculate the absolute value of error. I just provide a single example on a pharmacophore data set. We use different machine learning methods and descriptors, binary and count based from RDKit. We also implemented graph convolution method. We implemented the same interpretation approach as I described it before when we remove single atom. In this case, we just simply remove row from the matrix of atoms and correspondingly from the matrix of bonds. And we use the same universal interpretation approach to calculate all this contribution of all these atoms. So we remove them virtually in all these cases. And what we see is that here you can see accuracy of models, and here is the interpretation accuracy. And you can see that they correlate quite well. But another interesting observation is that even models which have relatively high predictive accuracy, the interpretation accuracy is not so high, so it can identify just about 50% of true centers. However, models have balanced accuracy higher than 0.8, what we consider usually as a good. So it's not so easy. See, here is another publication of Robert Sheridan, who also investigated this question on another data set. So you can refer to this publication as well. So now the questions appear, do we need new interpretation approaches? So of course, yes, we should do this, but we have to validate them. So we shouldn't take some simple approach, apply to our data set and say, okay, it works, or somehow justify the application. So we need to properly validate those new approaches which we took from computer science. Another question, what would be the main focus from which direction of research we can expect more advantages, which advance the field more? And here I would like to emphasize that we already can calculate the contribution of single atoms with multiple approaches. And I expect that the most important achievements would be related to development of new approaches which we are able to identify new types of knowledge, to extract something really new, not simply the contribution of single atoms. And the next challenge for us is introduce these interpretation approaches to the routine pipelines for medicinal chemists, just to guide them with their decisions. As the last, I just wanted to show two examples how these approaches can be applied. And this one is the interpretation of deep learning scoring function, GNINA, developed by David Coes, and they try to interpret the neural network model, convolutional model, and with different methods, and they try to somehow understood how it behaves, and finally it found that gradient-based methods, which are resulting quite similar to those with the silence, when they again virtually remove some part of a molecule of a protein. For linear-wise propagation, they discovered they do not correspond to those two other approaches. Unfortunately, they didn't make this analysis further, because I think that it is quite interesting that we were able to understand what's happening with those scoring functions, because everybody uses those scoring functions, which are now quite a lot of them are empirically based on these QSR models, but we are not happy with them. And these are the way how we can look inside, and maybe we were able to understand what is wrong with those scoring functions and to derive something new, to create something new. The last example is from our recent publication devoted to the multi-instance learning models. I will not talk much about this. I just say you that this is an approach which can use multiple representation of your molecule. In our case, we use conformers with 3D descriptors. The idea is that a neural network creates some embeddings for every conformer and then summarize those embeddings, but not in a simple way, but in a more smarter way using the weights determined by attention network, and then find the correlation. And the side effect of this method is that we get those weights which can somehow advise us which conformer is more relevant or less relevant to our modeling activity. In such a way, we can identify some bioactive conformers. We performed some experiments, built models on several data sets, and collected molecules which from test set which were in PDB data bank. Here is those yellow bars denotes an overall number of structures from PDB. Also, these dark orange bars identify the number of true poses which were found by RDKit simply. So RDKit generates really good conformers, biologically relevant, and quite often they could at least half of them or even more identify. And this light blue bar is the number of conformers which were identified by this approach. Of course, not in all cases we could outperform the baseline or docking or some other approaches, but in some cases we performed better than the random choice or even docking. So this is another example how we can retrieve something completely new, because we built models in a ligand-based setting. So we do not know the structure of a protein. We do not encode this feature of a protein, but we still can retrieve the bioactive conformers. It's quite interesting. And it's also, of course, it requires further investigation. So this is just a preliminary study that we show how we can use this. So at the end, I wanted to say there are a lot of hidden treasures inside those models. And this is our goal, to retrieve this knowledge. And we should do this in a mostly systematical way to evaluate our approaches, because quite frequently in the publications you can see that the researchers cherry-pick some examples, show them, discuss, okay, we observe some good correspondence for this particular atom in this molecule, we are okay, we are happy, but it is not really enough. It's not really enough. So that's why we provided those benchmarks, which should be, of course, developed more, so you can propose your own benchmark if you have some ideas how to improve them. Another, what we discovered, that interpretation depends on the predictivity. So you can interpret only highly predictive model. For moderately predictive model, you can observe some good interpretation, but it's not necessary already. So it may happen that your interpretation will be similar to random selection. And last but not least, but maybe the most important, that any model, in my opinion, are interpretable, at least nowadays. Even those complex deep learning with graph convolution, whatever. So we can find something, some knowledge. Whether this knowledge useful or not, it depends on us how to explain this knowledge. And sorry, I forgot to insert one more slide. That's quite strange. Sorry. I invited you to apply to contribute to the special issue of pharmaceutical journals from MDPI publisher, where we have a special issue on pharmacophore modeling. If you have some publication with new pharmacophore modeling techniques or applications, you can submit. The deadline for submission is the end of August. So thank you for your attention.
Thank you, Pavel. We have time for 2 short questions.
Sorry that this time travel was delayed a little bit.
Thank you for your great lecture. Regarding the benchmark research, I'd like to know what the important condition or parameter, something like machine learning algorithm or descriptors or a combination of them.
You mean what we proposed?
I remember you investigated.
Yeah, we investigated.
Yeah,
it is difficult to say which are more preferable or less preferable. I believe that it depends on the task. For this particular situation, atom pairs were the best one, but they're quite specific. Atom pairs encode very distant atoms on up to 20 bonds. That's why they were able to capture this pharmacophore hypothesis. Other descriptors, which are, for example, Morgan or graph convolutions, they are local and they cannot capture these distant features which were introduced to this logic. That's why they perform a little bit less precisely in interpretation. Models are also a little bit worse.
Okay, I understand. Thank you.
Last question.
So, Pavel, when you say, I want to capture the influence of atom A according to the model, that's nice, but deleting the atom A sometimes changes the pKa at the other side of the molecule, and that's not something you take into account. You only delete the bit corresponding to atom A. So all these interpretations can be, I mean, they're kind of mathematical games for me. In my opinion, the only thing that makes sense is to ask the model, how would property change if I do a step from the original molecule to another valid molecule? It's not like deleting the chlorine atom. I'm replacing the chlorine atom by a hydrogen with all the consequences that derive. And I think this is safer because you can do the mathematical interpretation, but I'm a bit suspicious about what it really means. What do you think?
That's a good remark. Actually, there is an approach which was later proposed by Igor Tetko, where he proposed to use computational MMP, matched molecular pairs, so you can calculate the difference between predicted values. But in this case, as well as in this case, you will struggle with the applicability domain of your model, so you cannot make large changes. And those removal of small fragments or atoms seems safe way, but if we add or replace some groups of atoms, this might already be outside of applicability domain. So these are games, these are not completely artificial because results are in a good correspondence with the expert knowledge. So it has some sense, but we still have to discover this question more, of course. To be not simply just those calculators.
Okay, so we have to stop here. Thank you again for